Okay, so far we've talked about ways of calculating heat when you have a hot piece of metal, put into some cold water, and the heat is transferred from the hot thing to the cold thing, the high temperature to the low temperature. That's one way, Q equals mc delta T. We've talked about how to calculate heat for a chemical reaction using heats of formation. Now the thing about the heats of formation is they have to be done at what's called standard conditions. And those are kind of hard to come by. Okay, particularly in Colorado, because one of the standard conditions is the standard pressure is 1 atmosphere. And in Colorado, it just never is 1 atmosphere because we're too high elevation. So there's a third way, and the third way is referring to something called Hess's Law. And this can be pretty complex. We're going to start off pretty simple, and I'll show you some of the harder ones as we go. And it's like a puzzle, and it's a different way of calculating how much heat a reaction has. Okay, like another reason why we do it is many times you can't create compounds directly from their elements. They have to come from other compounds and build up from there. So multiple chemical reactions take place. So what Hess's Law says is that the heat change. So we're calculating the heat, but again, since it's for a reaction, we're going to call it delta H, not Q. Okay, for a reaction that's carried out in a series of steps. So it's almost like a domino kind of thing. This happens, then something else happens. The way you find the heat for the whole thing is add up each of the delta H's for the individual steps. Well, that sounds pretty simple. And it isn't too bad, but it can be a little complex. So we're going to work through it, and we're going to start simple. So if I had H2O solid going to H2O liquid, that value, according to what we were doing before when we did phase changes, the heat for this value is the heat of fusion, which is 333 joules per gram. Heat has to go into the system. It is endothermic, and this value is actually positive. Now, we're not going to talk too much about the negative values for the heat, but the reverse reaction is exothermic, and since the heat is going in for the melting process, the heat is coming out, and heat for this one technically is negative 333 joules per gram. You can change the sign of it. And delta H has different signs. It's positive if the heat is going into, or heat has to be added. It's an easy way to remember. And if it's exothermic, it's losing heat, so delta H is negative. And again, if it's losing something, it's a net loss negative number. So that's going to help us a little bit when we're doing this. So if you reverse a reaction, it changes the sign of the delta H. And it is possible to use the same concept of Hess's Law and the concept of reversing reactions to find the heat of reaction for any reaction by using those steps that we talked about in Hess's Law. So in practice, you can add up several reactions. We're going to start with 2. We'll build up to maybe 3, 4, 5 tops, because the more reactions you have, the more complicated it gets. Okay, so the rules for Hess's Law. A reaction can be written as the sum, so we're going to be adding a whole bunch of numbers together, of 2 or more reactions for which the delta H is known. If you multiply a reaction by the coefficients by some number, say 5 or 2 or 4 or something, then the value of the heat is multiplied by the same factor. And you may remember I was talking about this with regards to, I think it was gas in your stove or something. If you use 1 kilogram of gas in your gas grill, you'll get a certain amount of heat. If you use 2 kilograms, you'll get twice as much heat. So the amount of heat is also multiplied by whatever the coefficients get multiplied by, okay, because it is the amount of heat you get is directly related to the amount of stuff you use. And this is going back to what we just talked about in the last slide. If you reverse a reaction, you change the sign of the heat. Instead of being positive 333, if it's exothermic, it's negative 333. And the reason why is reactions that release heat in one direction absorb the same amount of heat in the reverse direction, or vice versa. Okay, so some of the hints that will help you. The biggest hint is start with the first reactant in the desired equation. And you want to manipulate it in the given equations to make it match the desired. That's the idea. Okay? You're going to use -1 as a multiplier if you need to reverse it, because again, remember I said, if it's positive in one direction, it's negative in the other direction. So multiplying by -1 changes the sign of the delta H, and it reverses the reaction. That's the big thing. And then if you when you're doing this, if you run into a situation where the element or the compound is written in more than one of the given reactions, a good hint is to just skip it as long as you possibly can, because it makes it more difficult if you try to make it match, and I'll walk through that. And then at the very end, you're going to double check, and I'll show you how to do that. This is almost like, if you want to think of algebra class, there's a process in algebra called elimination in a system of equations. And that's essentially what we're going to be doing. Just like in algebra class, if you have to multiply an equation by a number, all the numbers get multiplied, and then they eliminate one of the variables to solve the system of equations. And that's essentially what we're doing, except it's a little more complex because it involves science. So here's the problem. It says find the heat of reaction for this reaction. Okay, but what I'm going to do is I'm going to give you a series of equations, and I'm going to ask you to take these two equations and manipulate them so that those two equations, and they're a system of equations, can be eliminated down to this equation. Now it sounds more complicated than it is, and so you really do kind of have to pay attention as I talk my way through it. Okay, so the first thing I'm going to do, the first hint I gave you guys, is take the first reactant in the desired equation and find it somewhere down here. Now you notice N2 is right there. Now the first thing you're going to look for, you're looking for two things. Are they on the same side of the arrow? And in this case they are. So that's good. That means I don't have to reverse the equation, because remember, reversing the equation changes it from being exothermic to endothermic, or endothermic to exothermic. The next thing you want to look for is, do they have the same coefficient? And in this case they both have a coefficient of 1. So this equation, everything in it is absolutely perfect, because the N2 and the N2 match. And so we're not going to worry about any of the other stuff because those two match. So I'm just going to put a little 1 here as a reminder that I have looked at it and I know it's going to work. I'm going to rewrite it down here so I can show you something in a minute. And the delta H is positive 180 kilojoules. Okay, so now I look at the next reactant given to me and I see it's oxygen. Now the next thing you want to notice about oxygen is that it's written in two different equations. And this is another big hint. If it's in more than one of these given equations, you want to skip it. All right, you're going to make your life miserable. You're going to give yourself a headache trying to figure out how to make those oxygens match that one, because it's not easy. It's much easier to skip it. You know what? I'm just going to pause on that one for right now. I'm going to go over to this one. And I see that I have two NO2s. And again, I'm looking for two questions. Are they on the same side of the arrow? Well, I notice my NO2s here are on the left side, and my NO2s that I want need to be on the right side. So what I'm going to do is I want to reverse this reaction. And that's essentially like multiplying by -1. Because what that does, remember, is when you reverse the reaction, you're changing it from being exothermic here, and by multiplying by -1, I make it positive 112, which is now endothermic. And so what a -1 does, or a -2 or anything like that, anytime you do a negative multiplier, what it does is it takes everything on the right side of the equation and puts it on the left, and everything on the left side puts it on the right. So I'm going to rewrite this. O2 plus 2NO goes to 2NO2. So all I did was reverse the reaction around, and I changed the sign. Okay, now essentially I'm done because I have done something with both of my equations. You don't have to go back and figure out the oxygen, and I'll show you why, because it's going to work on its own. So what I'm going to do is, just like in math class, I'm going to add these equations together. Okay, and just like in math class, we're going to treat this arrow like an equal sign. And if they are on opposite sides of the arrow and they're exactly the same, they will cancel out. So if I notice, my N2 is all by its lonesome, so it's not going to cancel out. But I do have two NOs on the left, and I have two NOs on the right. And since they're on opposite sides and they are exactly the same, they cancel out. But notice my oxygens. They're exactly the same, but they're on the same side of the equation. That means they add together. Well, I have one oxygen here, one oxygen there, gives me a total of 2. And that turns into 2NO2, and all I have to do is add these numbers up as well. So 292 kilojoules. And that's what they're looking for. Okay? So when you're solving these equations, you want to look at the first reactant, find it down here. If it's only written in one place, make it work. If it's written in more than one place, skip it and come back if you need to. And then look for the next one. And you want to add them together, but what they're looking for is they're looking for that number. This is more like a check your answer kind of thing. They want the number is what they want. Okay, so let's look at this one. A little bit more difficult. Okay, but again, we're going to start on the left one of the reactions we want. And I'm going to find C. Now I notice I have a C right here, and remember the questions are on the same side of the arrow and the same coefficient. Those are the two questions you want to ask yourself. Well, I have one carbon and I have, sorry, 4 carbons and 1 carbon. I need to make this thing have a coefficient of 4, so I'm going to multiply it all by 4, which multiplies the heat by 4. And I'm going to rewrite it. I've got 4C plus 4 oxygen goes to 4 CO2. Notice all I did was multiply those coefficients of 1 and the heat that goes along with it. And I'm just going to cross that out because now I know I've done something with it. All right, next reactant is hydrogen. And I see hydrogen here. So the question is it on the same side of the arrow? Yes. Does it have the same coefficient? No. I need to have a coefficient of 2. I'm going to multiply by 2. Everything gets multiplied by 2. 2 hydrogens plus 2 times 1/2. If you need to get a calculator, go ahead, but it is 1 oxygen goes to 2 H2Os and 2 times negative 286. So everything got multiplied coefficients by 2 and the heat. Okay? Now I'm looking at my last given chemical, C2H2. And the first question is the C2H2 on the same side of the arrow? The answer is no. That means I need to reverse this reaction, which is equivalent to multiplying by a negative. And I need to give it a coefficient of 2, and it has a coefficient of 1. So I'm essentially multiplying it by negative 2. The 2 is to multiply the coefficients. The negative is to reverse the reaction. So everything that's on this side gets doubled. So 4 CO2 plus 2 H2O goes to, everything on this side moves to that side, 2 C2H2, and 2 times 5/2 is 5 oxygens. Now we have negative 2 times negative 1300. Now just to prove that it works, remember what they want is they want the number. Okay, all those numbers added together. So 4 times negative 394 plus 2 times negative 286 plus negative 2 times negative 1300. Total answer is 452 kilojoules. Now what I need to do is I need to add this up. Make sure that it works. Make sure my reactions work. So 4C, 4C. 2 hydrogens, 2 hydrogens. Sometimes it helps to circle it. 2, those are called acetylene, 2 acetylenes. Now, I want to make sure everything else cancels out. Well, I see 4 CO2s on the left, 4 CO2s on the right, opposite and the same. 2 H2Os on the left, 2 H2Os on the right, and again, opposite and the same. And then I have a total of 5 oxygens on the left and 5 oxygens on the right. So that tells me I did do it properly. But again, what they're looking for is the number. Okay? So it's kind of a process. It's kind of a puzzle. It's a different way of finding how much heat a reaction has instead of using the heats of formation. Okay? Now this one's getting a little bit more difficult yet. But again, we're going to follow the same kind of procedure. We're going to look for our P4O10. And if you want to kind of follow along, you can do this in your notes. There's my P4O10. And remember, the questions are same side of the arrow and same coefficients. That's what we're asking ourselves. So, not on the same side of the arrow, not the same coefficients. I need to make the coefficient of this guy, which is 1, into 1/2, and I need to turn it around. So I'm going to do the turn it around part first because I know that's negative. But then I need to make this coefficient, which is 1, into 1/2. Negative 1/2 times 1 is 1/2. well, the negative reverses the reaction. So I'm going to rewrite this reaction. 1/2 P4O10 plus, sorry, not plus, arrow, 1/2 P4. Remember, it multiplies the coefficients, not the subscripts. Plus 5/2 oxygen, and it's now -1/2 times -623. Okay, and I'm going to cross it off because I've done something with it. Okay, now I'm going to look at my next reactant, PCl5. And I want to look carefully because I want to make sure it's on the same side and the same coefficients, and there's only one of them. So like, there's my PCl5. That's the only place I see it. I see a lot of PCl3s, but only that one. Okay, so what I want to do is I want to make sure it has a coefficient of 3, and I want to make sure it moves from the right side to the left, so I'm going to multiply by -3. I get 3 PCl5 goes to 3 PCl3 plus 3 Cl2, and it's -3 times 28, and that one's done. Okay, now I'm going to look for my next given, 5 Cl3PO, and I see Cl3PO right here. I need to have a coefficient of 5. They are on the same side of the arrow, so at least I don't have to do the negative thing. So 5 PCl3 plus 5 times 1/2 is 5/2. And if you're not good at fractions, you might want to get out a calculator, and you can use decimals. It's okay. 5 times 142. Okay, and again, I've done something with that reaction. Now you might notice, wait a minute, I haven't done anything with that top reaction. Okay, they aren't giving it to you as a distractor. They aren't giving it to you to confuse you. They're giving it to you because you need it. All right, if I was to add this all up right now, I do have this guy, and I have my PCl5s, and I have this guy, but everything else needs to go away, and it's not going away right now. And so what I need to do is make it go away, and this is what's called an elimination kind of process. I want to find something that I need to get rid of, and so I'm just going to pick this one because it's the first one I see. Doesn't mean it has to be that one, but that one's not bad. I want to get rid of that P4. It's not one of my desired ones. And so I'm going to look at, here's my P4, and I'm going to use this equation to make that P4 go away. And so in order for it to go away, they have to be on opposite sides. I have a P4 here and a P4 on the left side. They're already set up to cancel out, but I have to have the same coefficient as well. This has a coefficient of 1/2. That means this needs a coefficient of 1/2. And when I do that, I get 1/2 P4 plus 3 Cl2 goes to 2 PCl3, and it's 1/2 times -375. And when I add these all together, and again, what they're looking for is the number, but just to prove to you it works, my 1/2 P4s cancel out, my 5/2 oxygen cancel out, my 3 Cl2s cancel out, and then if you look at the PCl3s, there's 3 and 2 on the right side, and 5 on the left side. And so that's a way of checking yourself. If things cancel out, then you're all good. And then the answer is just adding those numbers together. Multiplying and adding. And I got positive 750. Okay. All right. One more. Another elimination one. This one's not quite as, it's a little confusing, but it's not too bad. So Zn, they match. Okay. And I'm just going to rewrite it. Zn plus 1/8 S8. All right, goes to ZNS, and it's -183.92. Why I have all these decimals, I'll never know. I should change those, because whatever, fine. All right, so that's done. Then I notice my next reactant is 1/8 S8. Well, I've already done something with that, so just skip it, okay? There's my oxygens. Now my oxygens are in more than one place, so I'm going to skip them. Don't try to figure them out. You're going to make yourself sick trying to figure them out, honestly. ZnSO4 and ZnSO4, 1, and I'm going to rewrite it ZnO plus SO3 goes to ZnSO4, and it's also -230.32 because we need all those important decimals, not. All right, so now I'm done with the stuff up here. But I've still got two reactions, and like I said, they're not given to you to, like, you know, waste typeface or something like that. They put them there for a reason. So my Zn I want to keep, this I want to keep, that I want to keep. The rest of this all needs to go away. So pick one. All right, and make it go away. So I'm going to just pick ZNS because it's the first one I saw. I could have picked ZNO, but I'll pick ZNS. So ZNS on the right side, I want this is the ZNS on the left side to cancel out, so I need a coefficient of 1/2, or multiply by 1/2, coefficient of 1. ZNS plus 3/2 oxygen goes to ZNO plus SO2, and it's negative 927.54 over 2. Okay, so that's done. And let's see what cancels out. ZN's gone, ZN's gone, ZNO, ZNO. But the SO3 and the SO2 are still there, and so are the oxygens. And I do want to keep some of those oxygens. So what I'm going to try and do is get rid of this SO3. Because again, it's the next one I saw. So the SO3 on the left, SO3 on the right, I need to make them go away. And they're on opposite sides already, but I do need a coefficient of 1 to make the SO3 go away, so I'm going to multiply by 1/2. I get SO2 plus 1/2 O2 goes to SO3, and now I've got negative 196.04 over 2. SO2's cancel out. SO3's cancel out. 1/2 plus 3/2 would be 4/2, which is 2 oxygens, which I want to keep. So it works. You just kind of have to work your way through it, and there are certain tricks that make it easy. The answer here is negative 976.03 kilojoules. Okay, so the tricks are, first thing you want to ask yourself, are they on the same side of the arrow? If they're not, that's where you're going to do a negative multiplier. Negative 1, negative 2, negative 1/2. It could happen. Then you want to ask yourself, do they have the same coefficient? Okay, and if they have the same coefficient, you're good. If they don't have the same coefficient, that's where you're going to multiply everything, including these delta H's, to make the coefficients match. And then just rewrite them, and they're looking for a number. But to check and make sure you did it properly, you should try and check and make sure things cancel out. The one thing you do want to watch out for, there is a difference between H2O gas and H2O liquid. And so you will see those phases written in next to all the chemicals. I didn't put any of the phases in here. I think I might have put in one liquid water. But that's important to pay attention. They are not the same thing. Okay, on the homework, you will notice that there's H2O liquid or H2O gas. They don't cancel out. Okay, it's important to pay attention to.